Hello, my name is Russ Burleson, and today I'll be covering Class 1 of Introduction to Waves for Crave the Wave. As you can see, my name is Russ Burleson, and my email is provided below. Today we're going to go over the wave overview, the types of waves. We're going to talk about the rules. We're going to talk about building a binder. We're also going to talk about some miscellaneous tips, and I'll give some recommendations for homework. So, what is a wave? From Wikipedia, a wave is any type of propagating dynamic disturbance from one or more quantities, sometimes described by a wave equation. So, a lot of people like to think of a wave as energy in motion, either completely energy, maybe it is something more matter based, okay, like it's something physical, or something that actually has characteristics of both. Usually we'll talk about mechanical and electromagnetic waves, but there's also gravitational, heat diffusion, plasma, and reaction diffusion waves. Waves can often be periodic, okay, which means that they continue at a certain frequency, okay? In other words, you'll often hear something sometimes referred to as hertz, which is 1/2 which means how many times a particular wave goes through in a given time period. They can also just be a singular event, like a giant tidal wave. Okay, and then sometimes it'll be a large wave accompanied by smaller waves. When it's moving in one direction only, it's called a traveling wave because you can actually see it moving one direction or the other. However, if let's say it's in a cavity of some type where it is bouncing back and forth against itself, or sometimes if we shoot two waves at each other, what can happen is that they can overlap, superimpose, and form what is called a standing wave. You see this quite often in musical instruments where you're looking for a resonance in a cavity. So, energy, whether it's water, sound, or light, generally moves in waves. So let's talk about the most important thing to know with waves is if you look here at this picture here, you will see that we have a wavelength, and then we also have an amplitude, we have a crest, we have a trough, okay? And these are the things that we normally use to describe a periodic wave, okay? We'll also talk about what the direction of the motion is, because a wave is usually moving one direction or another. And then the other thing is that you're going to hear us talk a lot about group velocity, where the velocity is equal to the frequency times the wavelength. And you'll notice here we often use V or nu in Greek letters, or sometimes it's an italicized V for velocity, and then F is usually italicized F for the frequency, and that will be given in hertz. Velocity is given in meters per second. And so therefore, the last thing, lambda, is the wavelength, okay? And I want you to notice that the wavelength is from the same point on the wave to the same point on another wave, okay? So in other words, it's not necessarily always going to be from the same, a lot of people will try to say, oh, it's from here, it's from the crest to the trough. No, it's from the crest to the crest, the trough to the trough. If it's a zero, it's actually, it has to go through until it's at the same point in the wave, okay? The other thing is that we'll talk about how a frequency is actually the inverse of the time it takes for that entire wavelength to go past, which is referred to as a period. Now, a lot of times when we're talking about the direction of a wave, okay, we're going to have a direction, or sometimes it will be referred to as a vector. So the key things to keep in mind, this shows a light wave, which is created by a single photon in this particular case. It has a wavelength. Its wavelength is going to be really small, like on the order of nanometers, okay? Couple things to keep in mind. Changes in amplitude do not affect the frequency or the wavelength. So what that means is if you've got a stereo and you're listening to your music, if you turn the volume up, you're increasing the amplitude, but it doesn't change the pitch. It doesn't change the bass of the treble. It sounds the same. It's just louder. And the same thing with a light. If I have a green laser, it's going to have the same frequency as it, a half a watt as it does at 1 watt. Okay. All I've done is increase the amplitude. I've increased the intensity. Okay. Now, one of the more common ones that we see today when we're talking about amplitude and strength is, hey, how many bars do you have in your cell phone? And that's just measuring how much power is my cell phone receiving from the tower. Now let's talk about what frequency means. What frequency mean is that is the time that it takes it's the inverse of the time that it takes for an entire wavelength to pass. The time an entire wavelength takes to pass is called a period. Okay. And 1 over that, or the inverse of that, is the frequency. Okay. So like a low frequency is something that would be like this. So this is like about 1 hertz. Okay. Something that's much faster has a higher frequency. Okay. And that might be 3, 4 times the frequency. Okay. And so what you'll notice here is that a shorter wavelength goes with a higher frequency, and a longer wavelength goes with a lower frequency. So they're inversely related. Okay. Now, instead of us always saying 1 over second for frequency, we're going to use the term hertz quite a bit. Okay. And it's named after Mr. Hertz. And basically, it is 1 over second. 1 over 1 second equals 1 hertz. Okay. And so let's think about what are some of the normal type of frequencies that we think about. Okay. If you think of auditory things, you might be talking about thousands of hertz. So it might be, from tens of hertz to thousands of hertz. I think if your ears are really good, you can hear up to about 20 kilohertz. Okay. As you get older, like me, your hearing isn't as good, especially at the high frequency. So you usually can't hear the high frequency stuff as well. Okay. Then you look at things like radio waves, okay, and they go from 100 kilohertz up to 1 megahertz. That's 1,000,000 hertz. So that means that 1 radio wave, when you're listening to it, in 1 millionth of a second, you get the full wavelength. And so in 1 second, you get 1,000,000 individual wavelengths. Okay. And so that's usually what's considered radio bands. Okay. And then you just keep going up. Okay. And eventually you get to light waves. Okay. And what you're talking about there is that now you're talking about terahertz. Okay. So if you think about kilohertz being thousands and megahertz being millions, then you've got gigahertz above that. Okay, and that's usually for your for your radars and for your microwaves, like your microwave oven. And then above that, you get into the light range. Now you're talking terahertzes. Okay, and it keeps going up and up. And we're going to talk about spectrum later. But what you'll notice is that the wavelengths for radio waves are much bigger. Okay, a radio wave could have 30 kilometers for the size of the wavelength, which is a huge wavelength. Okay, and that's because the speed of light is very, very fast in air. Okay, and that entire wave, okay, takes a long time to go there. But as you speed it up, as you go from the lower AM bands all the way up to the higher AM bands, the FM bands, and all the way to the end of the FM bands, the wavelength keeps getting smaller as the frequency keeps getting up. So let's talk about the different types of wave velocity. The number one we're going to talk about is phase velocity. Okay, and that's the rate at which the wave propagates through any medium. Okay, so you will see this nu equals lambda times f, where nu or v is the velocity, lambda is the wavelength, and f is the frequency. Now remember, I told you that the period is the inverse of the frequency. Okay, and the period's given in seconds. So if you wanted to do it using the period, you might say v is equal to lambda divided by t, where t is the period in seconds. So v is always going to be in meters per second. Now the group velocity is the velocity at which the overall envelope shape progresses. And what that means is that now we're not looking at the individual waves. We're actually looking at a modulated wave. Okay. And so we'll get a little bit into modulation later, but the key thing to keep in mind is that that is like a wave over another wave. Okay. And the equations for group velocity are well beyond the scope for this particular event. Oh, one thing I'd like to bring up is that you'll notice here on every slide, I have down below links that you can click on to actually get to the root data or get to the images, etc. So let's talk about the two major classes of waves. We're going to talk about mechanical and electromagnetic waves. Mechanical waves are an oscillation of matter. In other words, there has to be a medium. So like if I've got sound, which is a mechanical wave, it has to go through air, or it has to go through metal, or it has to go through some sort of matter for it to go forward. Okay. Another one might be an earthquake, a seismic wave. It goes through the ground. It has to go through something. If I have a string on a guitar, the string itself is the matter for which it progresses. Okay. Now, electromagnetic waves are a little bit different. Electromagnetic waves are electric and magnetic fields that are synchronized together, okay? And they actually can propagate without a medium, okay? So you'll see above here, we have a water waves, which are mechanical waves, and they require water, okay? And actually the top wave is a special type of mechanical wave called a surface wave. Okay. Down below here, we have a picture in 3 dimensions of what an electromagnetic wave looks like. And what you'll notice is that the orange fields here, these are the electric fields. Okay. And you'll notice as the electric field goes up, the magnetic field also goes up, but it's in a different polarization. In other words, if this is the Z plane here, then this is the XY plane here. Okay. So as it goes higher in X, it goes lower, let's say, as it goes higher in Z, it goes lower in Y, for instance. Okay. And what you do is to figure out the way that the direction is of an electromagnetic wave is pointing is you put one finger from your right hand, your pointing finger, in the direction of the electric field. Okay. You put your middle finger at a 90-degree angle, okay, in the direction of the magnetic field. And then whichever way your right thumb is pointing, that's the propagation. So you'll notice if I put my pointing finger from my right hand up, and then the middle finger from that same right hand at 90 degrees, it's going to be pointing sort of towards me. And so my thumb goes to the right, and then you can see that's how that particular electromagnetic field is propagating. So let's talk about mechanical waves first. Okay, those are usually the ones that you've seen a lot more of. And so we're talking about oscillation of matter. So we're talking water, sound, seismic, etc. There's going to be an elastic and inertia-based medium to propagate. Okay. Now, elastic means it actually has to be able to move. So if you actually supercooled something down to absolute zero, and it can't move, it can't propagate a mechanical wave. Okay. The other thing to keep in mind is that if you took away all the matter, let's say we go to the vacuum of space, or which is sometimes we like to refer to as free space. Okay. So if you're out in outer space, the reason why the tagline for the movie Aliens was they can't hear you scream in space. It's because there's nothing for the sound wave to vibrate. So it doesn't propagate. So when you're watching Star Wars or Star Trek and they blow up a ship, if you were to see that in space, you'd never hear it. Now you could hear anything within your spacecraft because there's air for it to propagate. Okay. Now look, there are three subtypes of mechanical waves. There's transverse waves, there's longitudinal waves, and surface waves. So let's talk about transverse waves. So in this particular one, transverse, the medium vibrates perpendicular to the direction of the wave. Okay. So what this means is that if the wave is coming towards you, exactly normal to that, or perpendicular, or another term we like to use in 3D is called orthogonal to that, that's where the energy's going. So like if I was to take a rope and I was to fling it, like in this case up above here, a string wave, the energy is actually that deforms the string is going up and down, but the wave itself, okay, the wave itself is going side to side. So they're orthogonal to each other. Now, a longitudinal wave is the medium vibrates parallel to the direction of a wave. So what you'll notice here is that this is what a sound wave would look like. And you'll notice as that sound wave goes across, it pushes the matter together. And that's how the sound wave propagates. So in this particular case, the energy is going side to side and the propagation is side to side. So that's why it's a longitudinal wave. Then a surface wave, it requires two separate media. And at that interface, there is some type of wave propagation. So this could be something like a water wave, an ocean wave. This could be an earthquake or a seismic wave. Okay. And, if you think about a water wave, it's between the water and above it is the air. If I think about seismic waves, I've got ground, okay, which somewhat gets liquefied during a seismic wave, gets broken up. And then above it, I have air. One thing to keep in mind with electromagnetic waves is that they only move if the electric and magnetic fields are changing over time. If you just have a static or a DC electric field or a DC magnetic field, it actually doesn't produce a wave. But if you move that, like if I take a magnet, like the type you have on the side of your refrigerator, and I just don't move it, I'm not going to create a wave. But if I move it up and down, it's actually going to induce an electric field. Okay, because I've got a change in the magnetic field, and so it's going to induce an electric field, which is going to be orthogonal to it. Okay, and you can do the same thing with an electric field. If I have like an electric field, okay, and it's static, it's DC, it's not going to produce any waves either. However, I put that into the AC wall, I can now propagate a wave. That's why every radio is going to have a frequency, okay? Because for the waves to propagate from a sender to a receiver, there's got to be some type of oscillation. And when we talk about electromagnetic energy, we're always going to be talking about the electromagnetic spectrum. And the electromagnetic spectrum basically goes from almost DC, okay? So we're talking very low hertz, okay, all the way up to as big a number as you can think in frequency, okay? And then above that, okay, there's actually no upper end of the limit. Although for the most part, we can't measure anything above gamma rays. And in fact, a lot of gamma rays we can't measure because they're just too high a frequency. So what you'll notice is that if you go to Google and you type in electromagnetic spectrum and you click on the images tab, you're going to get literally thousands of little diagrams like you see here below. Okay. I would recommend in your binder to have the top 20 results of electromagnetic spectrum. Why? A real easy question for an event supervisor to ask you is that they will give you an electromagnetic spectrum diagram, ask you to fill it out. They'll white out the various portions of it. And if you've got that in your binder, you can copy it verbatim. Okay. They're not going to look beyond the first 20 most of the time. And even then, if you know the electromagnetic spectrum pretty well, you'll be able to fill in the blanks yourself. But you'll notice here, it'll go radio, microwave, infrared, visible light. So this is infrared light, this is visible light, and this is ultraviolet light. Okay. Above that is X-rays, and above that is gamma rays. Okay. You'll notice that the wavelength starts here in kilometers, right? Which we talked about. And then for microwaves, we're talking about centimeters. Okay. Then for infrared and visible, we're talking about 1/1,000,000th of basically a micrometer or a nanometer. Okay. And then in ultraviolet, now we're getting into all the really low numbers. That's 10 to the 8th, 10 to the minus 10, 10 to the 12th, or minus 12 for wavelength. And then you'll notice for frequency, it goes from 10,000 to 10 million, okay, to terahertz, and everything above that. Okay. And they try to also give you an idea of how big these wavelengths are. So the lower end of the radio waves is like building size, and then the upper end of radio waves is like human size. And then microwaves, their wavelengths is usually on the order of the size of a bee. Infrared, you're talking about a pinpoint. So like you take a pen like for sewing and you stick it in a piece of paper. That's how small the wavelength can be at the low end of infrared. And then once you get into visible, now you're talking about a single wavelength there is the size of protozoas. So we're talking like stuff you have to look at with a microscope. And then you get into ultraviolet, X-rays, and gamma rays, and you're talking about things that are much smaller than we can even imagine. They're the size of molecules or atoms or atomic nuclei. The other thing to keep in mind is that these are basically the same diagram. They're just written differently. But you'll notice they generally say the same things about radio, microwave, infrared, visible, ultraviolet, X-ray, gamma ray. They'll usually have a wavelength, and they usually have a frequency, and they'll show you where the visible light is, because that's something we can usually wrap our head around pretty easily. But knowing the normal upper and lower boundaries of these is very important. It's a very common question. The other thing is that when you get into visible light, know that you start with red, and it keeps going, orange, yellow, green, cyan, blue, and then up to violet, and then ultraviolet. It's important to know how those colors go, and you'll notice that they match exactly how a rainbow goes. And we'll get into that later when we start talking about refraction. So one thing to keep in mind is that light waves are electromagnetic waves. So even though they're created by these photons, which are these individual particles, these particles act like waves. They're both matter and waves. And there are a couple of things that have that dual capability. And so again, when you're looking at these electromagnetic spectrums, it's important to remember that sometimes these are pure energy waves, and sometimes they'll have something like a photon or an electron. All right, so let's talk about what I want you to do before the next class. And then what I'd really like you to do is start working on your binder. I usually recommend about a 2.5-inch binder. I'm not going to go through everything here, but just keep in mind, number one thing, use your binder every time you're studying Science Olympiad. So anytime you're watching these videos, anytime you're doing things, you're taking practice tests, studying, etc., use your binder. Okay? You build and you add to it. Make sure you really organize it well. Now, the way I would organize it's going to be different than the way you organize it. But you need to organize it where you can find anything in that binder in under 10 seconds. So you might use tabs. And then if you've got something like these really nice pictures that you're going to be going to a lot, or you might have a formula sheets or whatever that you go to a lot, you might put protectors on there. Focus on the things you have to look up or don't understand. So like if there's a particular type of problem that you see that they have on a lot of these tests, but you're really struggling with it, put a lot of examples of that problem easily to find, such that if you get that problem on the test, you can then go to that part of your binder and find it quickly. Make sure you've got all the tables for all the constants, materials, and equations. And again, 2.5 inches. I don't want to see a 6 or 8-inch binder because they'll be too hard to find stuff in. If there's some really good tests in there, include those in, but make sure you include the keys and the work shown. So that way you'll know how to solve the problem. Because even if I reused a test question, I'm probably going to change all the numbers. So you can't just copy the same answer. And you really need to understand how they came to that answer. Make sure you can read it. Okay. My eyes are not nearly as good as a lot of the people who are watching this who have very young eyes. However, there's some folks, even when they're young, have tougher time seeing than I do. So we might use different fonts. I might use a different color scheme than you would. Use what works well for you. Also, remember, it's a binder event, so there's really no limit. So if you see 2 pictures and you're not sure which one you want to go with, use both of them. Put them both in there. And when you solve a difficult problem in a way that makes sense to you, put all the steps in there and keep it in your binder. Okay? Start and end every practice session with a binder check to see if you can find stuff. And you and your partner can actually quiz each other and see if they can find stuff. And remember, if you can't find it in 10 seconds, you didn't find it. And that just tells you need to keep working on your binder. I can't emphasize this enough. Read the rules. The rules will be released the Tuesday after Labor Day. Okay. The official ones are at soinc.org. Okay. At the Science Olympiad National website. Okay. Also, check back for rule clarifications and FAQs. There's usually not too many in Crave the Wave, but you know what? Still, it's a good practice. And I like to put the rules as the first page in my binder. That way, if I'm going to argue in a legal question or I have a question about whether or not this is a legal thing, I can go back to that. Okay. I would also recommend going to scioli.org. Great reference, but it's a student-run website. So these are not official, and it can contain errors and old information and a lot of opinions. I also recommend when going to Scioli, be very, very careful. Don't get caught into an argument with somebody else. So let's talk about Crave the Wave rules and scoring. It's a 2-person team. You can bring your binder, writing utensils, calculator, protractors, etc. They're going to try to do some hands-on tasks. Now, if you're doing a virtual tournament, they ask the same questions they would with a normal hands-on task, but it's pretty much all written at that point. No single question is going to be more than 10% of the score. High score wins. You see over here the topics, some of the big changes, okay? Earthquake and seismic waves are now available and are things that you would have to cover in we call it at regionals, okay? So that one's been moved up, okay? The other thing is that Doppler and Snell's law calculations have now been moved back to state and nationals only. Okay, that's because there were some trigonometric functions, and we tried to listen to the feedback from folks. However, asking questions about refraction and the Doppler effect is still legal. okay, even at the regional level. Boundary effects remain at the national level. Here's some miscellaneous tips. Here are some suggested resources that you may want to look at. I use Wikipedia quite a bit, but there's a ton of other ones at Sonic. I will tell you, I use Britannica quite a bit. Khan Academy's got some great explanations of various things. I've included in here some great links. And as you see, it just continues. My recommendation is always look for the reference that makes the most sense for you. Okay, so the same thing that I might like to use might be something different than what you would. And the last thing is winners prepare. No one was born knowing wave theory. Okay, so what you do is you study and you do homework before practice. That way, when you're at practice, you're just really focusing on asking questions of your coach, and you're not wasting time having them watch you read. Okay. Plan on doing work on this a few times in a week in addition to practice. So I like to treat practices as a time that you're going to be taking practice tests, etc. So it's like it's a test, so prepare. Be a good partner. Work off each other's strengths. Maybe you're very good at calculations. They're very good at being able to visualize it. Okay. Or everybody's got different strengths. Find out from your partner what they're best at and practice together quite a bit. Learn how to check each other's work best. Keep in mind, event supervisors are volunteers. So this means that they've taken their own time to do this. Okay. Some are going to be more experienced than others. Some are going to know the rules better than others. Honestly, some are going to be better than others. Okay. So be respectful and work with them. And what you usually find out is that they're going to be respectful and work with you. Okay. Listen to the instructor. This is super important, especially on virtual tournaments. I can't tell you how many times I got frustrated by students who would ask me how many significant figures when it said 3 significant figures. And then I would answer for that question, it says 3 significant figures. And somebody else will come back and say, how many significant figures? After a while, I stopped answering. So if the people had just listened to me at the very beginning, they would have known that answer. Okay. Also, keep in mind, different event supervisors are going to ask the same question differently. That's why you want to look at a lot of different old tests. If you're going to argue an illegal question, the first thing I always recommend is reread the question, reread the rules to make sure you know exactly why it's illegal. The event supervisor could have the old rules, but double check those rules you got in your binders, the brand new ones. Okay. I like to always ask the event supervisor, hey, how can I implement it within the rules? Okay. And reference the specific rule. Don't just say it's in there. Okay. Remember, they're trying to manage an entire class of anywhere from 20 to maybe up to 200 teams. Okay. Most importantly, do not stop working the test. I have seen people wreck an entire test arguing a 1-point question, and then they ran out of time and they never got to answer 10-point questions. So even if they win the argument in arbitration, they might get that 1 point, maybe. And that's pretty rare. So in other words, ask the question, get the answer, and then keep moving. Okay. If you're going to do an arbitration, do that later. So what I'd like you to do before you go to the next one of these is to select a 2 to 3 inch binder and develop it for Crave the Wave. Print out the rules, put it in the first page, put in your equations, get a whole bunch of materials. I gave some Wikipedia links here, but get some other ones as well. Okay, be ready to find any rule, any definition in the frequency range for any electromagnetic wave. Okay, in other words, what's the range for green light? What's the range for X-rays? Be ready to answer those questions quickly. And this completes the first class.